Okay, so here we are. We've already covered architecting fundamentals. We've already talked about account security. Now we're moving down into networking, right? So the first of networking. So the check-in question here is basically what percentage of your workloads are publicly accessible? Now, again, interesting questions that AWS asks here, because I don't think most people know like what percentage of their workloads. But as far as like your individual processes or products, is anyone running anything that is now publicly accessible over the World Wide Web? Cool. That's a rarity, Christian. So yeah, good to know. Well, at least at Booz, right? Most of the stuff is semi-private, but that's good. Okay. Well, we've got one. All right, so let's talk about networking then. And so here's our kind of like feedback here. We're still focused on security, which by the way, was the #1 objection to cloud back in 2010. So I could argue that first and foremost, AWS is a security company. So what we want to do is we want to isolate and secure resources with our design, but we also want to build highly available networks. We want to support IPv6. And how do we like control access? How do we filter access to layer 7, layer 3, and 4? How do we do that? And so our questions are, how do I build a dynamic and secure network infrastructure in my accounts? How do I divide my private cloud into subnets and assign IP addresses? And how can I direct and filter traffic that is moving in and out of a network? Now, here we are, we're starting to build the pieces of this diagram that we talked about in very early on in module 1, right? So here we are, we're actually going to talk about the public subnets, the private subnets, the NAT gateways, and their internet gateway. And notice there's a region with a VPC around it. We're going to start talking about this. So we're going to talk a little bit about IP addressing, a little XOR notation, and we're not going to get too far into this. And I'm just going to skim it. I will tell you that kudos for people who are network engineers, because the network engineering exam, I hear, is one of the toughest specialty exams to take in AWS. But most of them really like that kind of thing, so most people don't shy away from it. And then we're going to talk about the fundamentals of a virtual private cloud, which is what VPC stands for. And then we're going to talk about a little bit about traffic security, like how do you secure at a core level traffic inside of AWS. So how do we deal with the fact that we're going to run out of IP addresses, by the way? Well, first of all, let's compare IPv version 4 with IP version 6. So note that we're all used to IP version 4, right? It's our 10 addresses, our 192s, our 172s. These are the 4 numbers that range from 0 to 255. That usually has a slash and then a number after it, which denotes what portion of that is the host network and which portion of that is the actual network definition. And so notice that with IPv4, you're either using a 10 address, a 192.168, or a 172.16 to a 172.31 range, right? You're for private IP addresses. And we're used to this because most of our homes are using like a 192 or a 10 or some other kind of network. So IPv6, by contrast, doesn't have those little private IP ranges like the 10s and the 192s. Every single IP address on IPv6 is internet routable. But let me put this in perspective. When they came up with IPv4, it had 4.3 billion addresses, possible for it. And they were like, there's no way we're going to get to 4.3 billion IP addresses. IPv6 supports 340 trillion addresses. So as you can imagine, IPv6 supports a lot more, and it has no private ranges because it has so many IP addresses. So IPv6 would be the way to go if you're doing something now, right? Amazon global unicast addresses, internet routable. Yeah. So basically, when you get an IPv6 address, it is part of Amazon's kind of unique range, right, of global unicast addresses, right? So I don't know if there's any like much more to say about this, except that just know that even if you only needed IPv6 in Amazon, you can't disable IPv4 because it's like the enabler for how they manage most of their infrastructure. So you can't disable IPv4. You always have to keep it. And most people are still using IPv4 and they're bleeding over into IPv6. No, I know. I know, Christian. I hear what you're saying about not being a true cider. I know. I get it. But we're gonna skip over that for a minute. Notice I didn't mention that. All right. If we're talking about IPv4 and not IPv6, just be aware that what we're doing here is that little slash denotes whether we're talking about the whole range, right, as far as like host IP addresses go, or whether we're talking about the specific number, or whether we're talking about a certain section of it. So think of each of those, like in between the periods, those numbers, think of them as 8 bits because they are 8 bits, right? And so when we say a /16, we're talking about half those numbers because 2 of those little sections is 8, right? If we're talking about /24, we're talking about 3 of those sections, which is like the 10.22.33. So just trying to simplify that down because we're not going to go into subnetting and XORing and all the whole 9 yards, right? We're not going to do that. Here's what you need to mainly remember is that Amazon will let you run a network CIDR range with IPv4 from a /16 to a /28. The higher the number, the smaller number of hosts you can put on the network. So a /28, as it lists here, will only host 16 IP addresses. But we're going to add insult to injury and tell you that if this is a subnet, you're going to lose 5 IP addresses because Amazon's going to take 5. Well, 2 are taken by the network, but 3 are taken by Amazon. And so you'll actually end up with only 11 usable IP addresses if you run a network as small as a /28. If you run a network as small as a /16, you're going to lose 5 IP addresses. You're not going to care because it's 65,531. So you don't care, right? So just know that that little number, the /0, means any number here. /32 means these specific numbers, and a /24 means any random number at the end of that octet, and a /16 means any random number at the 2 ends of that set, right? So that's the best way to think it. You can see it actually visualized there. In other words, they put a wildcard there, which means a /24 could mean any number in that range from 0 to 255. But I do want to point out, by the way, that you do lose 5 IP addresses on any network with AWS. The first one, the last one, actually, I'm sorry, the first 4 and the last one. So if 0 to 255 is your range, you would lose 0, 1, 2, and 3, and then you would lose 255. So just note that you can specify different ranges of IP addresses, up to 5 different sets, if I remember correctly, per virtual private cloud. And you might say, Michael, what's a virtual private cloud? Virtual private cloud is when you actually subdivide your AWS account into a networking pie. That's the way I like to think of it. It's like a pie, right? And what you subdivide it into is it could be a 10.0 pie, it could be a 10.1 pie, it could be a 10 pie. Well, actually, that's not true because it's /16. So 10.1, 10.2, 10.3, 10.0. It could be a 192.168 pie. My point being is that you're going to assign a number to your pie, and that's going to inform the networks that you create with the VPC. Now, the networks you create with the VPC are called subnets. And we're going to talk about VPCs in just a second. But the main thing you need to know is that when you create a subnetwork inside of a VPC, you're creating slices of this pie. Well, the slices are either going to be privately enabled or they're going to be publicly enabled. And what's the difference? The difference is whether or not that subnet can actually talk to the internet or not talk to the internet. And there's 2 pieces for that. It has to have a public IP address and it has to have connectivity to the internet. So we're going to talk about what those structures are that create connectivity to the internet. But just know that you can create networks on Amazon that have no connectivity to the internet, no direct connectivity to the internet. And you can create other public subnets on Amazon that have direct access to the internet, and the internet has direct access to them. Now, a word of caution. Everything we do in AWS is secure by default. I say we as if I work for Amazon. I don't. But my point being is that we as customers, everything we do inside AWS is secure by default. So when you launch an EC2 virtual machine and you don't put holes in your firewall, it's locked off from the internet. So just know that things like that exist by default to prevent you from hurting yourself by overexposing yourself to the internet, which of course we all know is not the safest of places, even though it is an enabler. So remember that even if you are using public IP addresses, you are protected unless you open yourself up to the internet. So that's just a few fundamentals around IP addressing inside of AWS. One other thing worth mentioning is that every single resource inside of AWS, whether it's on a public network or private, gets a private IP address. So just be aware that Amazon does provide a public IP address for everything, even if that thing has a public IP address. Okay, and that's just how Amazon it manages all the resources, like particularly the virtual machines and stuff. Okay, that's just a little bit about IP addressing before we actually get into VPC fundamentals, where we talk about subnets, we talk about internet gateways, we talk about route tables, we talk about NAT gateways, we talked about network interfaces. Anyone have any questions? Let's see, Christian, the reason you lose, so you use first and last, and then you lose 3 more. The reason you lose 3 more is because of DNS, routing, and reserved, right? They just reserved the first 3 IP addresses in every space. So DNS, routing, and experimental. Good. Okay, it's currently 12. So here's what we're going to do. We're going to come back at 1:03. Repeat after me, 1:03. So we're going to come back at 1:03. I'm going to pause the recording. When you come back, we're going to do some VPC fundamentals, and then we're going to cover the last section. And then we've got like 1 or 2 more lectures, and then we're going to do a lab at the end of the day. Okay. So I'm going to put a timer up, but in exactly 62 minutes, you're going to come back from lunch all refreshed because you went and played in the snow and got a glass of water and visited with your family and did some Christmas wrapping or holiday wrapping or whatever it is you celebrate, which I hope you have a happy holiday. But we're going to be back in 62 minutes. Okay. So we'll see you then. I'll put a timer up. We're going to talk about VPC fundamentals. Does anyone have any questions about anything we've covered this far? Okay. All right, so let's get into some details around VPCs here. So we're going to talk about the different components that make up core networking inside of AWS. All of these discussions start with kind of one key facet, which is basically the VPC, the virtual private cloud, right? VPCs provides like a network and logical partition basically to kind of segment resources like services inside of a single region. So VPCs live inside of a single region. They do not span regions, but they eat the entire region. So when you stick something inside of a VPC, you're running it for the most part in availability zones that are inside the region, but the VPC itself is region spanning. It eats the whole region. Now, by the way, you can use IPv6 or IPv4 in your regions. It's basically a virtual network. Well, what happens is we take these virtual networks and we subslice them into subnetworks, right? Subslice them. That's a weird phrase. We slice them into subnetworks. So here, those subnetworks have to live in one and only one availability zone. So while VPCs can go across the entire region, when you slice them into actual subnetworks, they live in one availability zone. If there were 6 availability zones here, and we wanted to run 6 virtual machines, each one of those availability zones would either have a private or a public subnet inside of it, because anything with a network card must go inside of a subnet in AWS. So it's not like we're going to pull in, we can't run it at a VPC level, right? It basically has to run across, inside of an unavailability zone. So in this particular case, we would run a virtual machine like here in a public subnet, and we'd have to run another one for redundancy, or we could run a database in a private subnet and another one here for redundancy. That's if we're using EC2 virtual machines. Anything with a network card is going to need to be stuck typically inside of a subnet. And you might say, well, Michael, what else other than virtual machines has a network card? Well, containers can have networking attached to them. Lambdas can as well. You can also run what's called VPC endpoints, which are like virtual network cards that are used for different purposes. So basically, if it has a network card, it's going to have to go into a subnet inside of a VPC. That's the bottom line. Now, when we use subnets to divide our VPCs, right? Let's say our VPC has a classless internet domain routing name of a /22, which means that it has 1,024 addresses. What happens is that we can split that up into 251 addresses by subnetting that even further, right? Now, I want to just point something out here is that note that normally that would be 255 addresses, but you're losing some addresses here, right? You're losing addresses, right? So when you create a subnet, you lose the first 4 addresses and you lose the last address. So for example, in this case, let's say it's a 10.0.0, right? What would happen is that if a 10.0.0.0 was like your kind of like network prefix, you would basically lose the first 4 addresses. So 0, 1, 2, and 3, and then you'd lose the last address was a 255. That's if it was a clean, right? We'll say a /24 as an example, right? I don't know if it's /22. Does that make sense here? Let me just think about this for a second. Yeah, I guess that would be, right? A /22 would give you 1,024 addresses. Then you would subdivide them into /24s. So they give you the 4 ranges in question. Does that make sense? So just something to be aware of is that you're going to lose 5 usable IP addresses off the set, right? So if it's a /24 and it ostensibly has 256 addresses, you're going to lose 5, right? If it's a /21, which has 20,048 addresses, and you decide to sub that out, you're going to lose 5 out, right? So just remember, you're going to lose 5 IP addresses when you subnet something. Okay, so you've got a VPC. It has an IP range attached to it. And by the way, you can add IP ranges to a VPC. So a VPC could have multiple IP ranges attached to that singular VPC. When you create subnetworks, you're taking slices of those IP ranges and you're creating little subnetworks off of that. You're going to lose 5 IP addresses off your subnet. Now, once you've fashioned your VPC and you've got subnets inside of it, some of those subnets are going to be connected to the internet. Some of those subnets are not going to be connected to the internet. If it has a path and connection to the internet, it's called a public subnet, which means that it has the potential to get to the internet and the internet has the potential to get to it. If it does not have connectivity to the internet, it's called a private subnet. Private subnets do not have a path or map to the internet gateway, which is the virtual device inside of Amazon that grants you access to the internet. Now, don't be fooled. You're going to sit there and think to yourself, man, this internet gateway looks like a single point of failure. It's not. It's actually multiple virtual devices like underneath that internet gateway endpoint. So even though it looks like a single device, it's not. Those things scale up and down like pretty rapidly. I don't know that I've even come close to overpowering an internet gateway. I don't know how many terabits it is per second, but it's a lot. It's a lot. If you go in the console and you check this out, let's say we go to VPCs here. By default, just so you know, in every account, there is a default gateway. Sorry, there's a default VPC and a default subnet and all this other stuff. But if we go over here and look at internet gateways, notice that I've only got one here because I only think I have only one VPC in the Ohio section. And if we look at this gateway, right, there's not a whole lot to it. There's the internet gateway name. Here's the associated VPC ID. And the way this works is that, here's the account owner, just to be clear, is that the only thing I can really do is attach it, detach it, and manage the tags. That's it. Otherwise, there's not a whole lot you can do with just a plain old internet gateway because it's just an egress point, if you will, for IPv4. So one other thing to note is that the reason that these two are linked together, the internet gateway and the VPC, is that it's associated with it. But if I look at this route table, you'll notice that that internet gateway is listed as the default destination for any traffic that doesn't match any of the preceding traffic. What this means is that if I put a subnet on this VPC, it's going to inherit this route table. And this route table says, if you don't know where the traffic is because it's not on your network and I don't have a mapping for it, I want you to send it to the internet gateway. And the internet gateway in turn is going to send, it's going to go talk to the internet. That's what it does. So just keep in mind is that it requires the internet gateway to be associated with the VPC, and it requires a mapping inside the route table that says, hey, if you're looking for traffic that isn't local to you, go talk to the internet gateway. That's what makes this a public, like in a sense, like VPC, although there's subnets here, right? So let's go look at a subnet. So there's subnets inside of this VPC. Now notice that these are 172 addresses. If we go back and look at our VPCs, notice how it says 172.3.1. If we go back and look at our VPCs, notice that this says 172.3.1 as well. Because this is the pie, so VPC is the pie. The subnets are slices of the pie. So notice this is a 172.16, this is a 172.0, this is a 172.32. Note that, by the way, there's different hash ranges assigned to that. It's like for a /20, right? Which is kind of funny. Let's see, a /20 would be what? 512, 1024, 2048, 4096, I think it is, would be. Is that right? Yeah, that sounds about right. 4096 addresses. If we go look at the route table for just this first subnet as an example, let's go look at the route table here. If we go look at this route table, I just want you to note that under routes, it says the internet gateway is the default path for any traffic that I do not know. In other words, if it's not 172.31 traffic, meaning it's local, because that's what it's going to do, is it's going to look for it locally, it's going to assume that any other traffic, which is what that 0.0.0, those are all wildcards, right? That's what that 0 represents with a /0 on the end. Those are all wildcards. That means that any traffic that is not local, that's not 172.31 traffic, is going to route to that internet gateway. The internet gateway is then going to go out to the internet and try to find out where that traffic should go. So it's an association and a route table entry that is associated that makes a public subnet a public subnet. It has to have an internet gateway attached to it, and it has to be findable. Now, I say an attachment. The internet gateway is attached to the VPC, not to the subnet, right? Because the VPC wraps around the subnets. So as long as the subnets are inside that VPC and there's an internet gateway there, they can talk to it.
Question for you.
Yeah, go ahead.
So the CIDR range, the first destination, the 172.31.0016, is that for the subnet, this particular subnet, or what is that, or VPC, or
That's the whole VPC.
whole VPC?
So that guy can talk to any other subnet that's inside the VPC. That's the default behavior, by the way. So by default, subnets inside of a VPC can talk to each other.
Gotcha.
Does that make sense?
So which traffic, right, sir? So I'm trying to understand the second line there. As you said, like if doesn't match the other one local, then it, route to internet gateway. Which one will not match? Like
any 172, any traffic that starts with 172.31 is not going to match that, so it's not going to get routed to the internet gateway. All other traffic is going to get routed to the internet gateway.
I see.
Yeah. So anything that's not a 172.131 is going to go here and then get routed here.
I see.
So basically everything. Now this is a very simple route table, as I'm sure anybody who's, yourself included, who's administered route tables can tell you. I mean, there can be 1,000 entries in here about where to send traffic, right? 192 traffic can go over here, 10 traffic should go over here, 54 traffic should go over here. There can be a lot of entries in a route table. And this one is just 2 entries, right?
Nice.
Local traffic and anything that's not local goes out to the internet.
And here by local means what?
Anything that's a 172 traffic. Oh, you mean what does local mean?
Yeah.
It means it's a subnet inside the VPC.
Oh, gotcha.
Yeah, it's local to the VPC.
Okay.
This is the reason, by the way, you can't connect 2 VPCs together that have the same network range. Because they both have route tables that'll look like this. And so if you try to talk to a 172.31 box, it thinks it's local, and so it won't route you to that system. So there are ways to force it to do something different, but they're all very tricksy. Okay. So public subnets, private subnets, the difference is that can your subnet talk to the internet? Does it have a route to the internet gateway? Now, note that the one other thing that you need in order to talk to the internet is you have to have a public IP address. So notice that in the public subnet, the EC2 instance doesn't just have a private IP address. It also has a public IP address. So for an EC2 virtual machine, for an EC2 instance, that's the third thing you need. So not only do you need to be on a public subnet that has connectivity, you also actually need to have a public IP address associated with that EC2 instance. If it does not have a public IP address, then it can talk to the internet, but the internet, really can't get inbound to it, right? You can't initiate connections into it. So general rule of thumb is do not stick any of your virtual machines on public internets. Man, just over here making stuff up now at this point. Oh, do not stick them on public subnets. Put a load balancer or some other kind of ingress device into the public subnet, but keep your EC2 machines on a private subnet as much as possible. Let AWS defend the load balancer or whatever other ingress device you're using. Let them defend it, and then you can just focus on keeping all your stuff on private subnets. Okay. Now, we already talked a little bit about route tables. So you already saw me go through and say, hey, make sure that your route, if it's attached to the, internet gateway, it's going to have an entry in the public route table that says, hey, by the way, send all your traffic here. Note here that the private route table is not going to have any default route to an internet gateway. So you can see down the lower right-hand side, that private route table has no entry for the internet gateway attached to it. So, to say this is that there is an invisible router here, which is what the route table is actually accomplishing, is that it's routing based on the rules that you specify. Every subnet inside of a VPC has to be associated with the route table. It can either be the VPC's route table, or you can create your own custom route tables for each of your subnets. A subnet can only be associated with one route table at a time, but you can have multiple subnets all using the same route table, right? So just know, like, it's like a many to one relationship. A bunch of subnets can be use one route table, but you can't attach multiple route tables to a single subnet because that's just confusing. There should only be one path out from a network and one map to look at to get out of that network. And so that's what a route table is. A route table is a path, to and out, in and out of the network, right? If you got multiple maps to get in and out of the network, it gets confusing. So now, route tables are important because they're going to control how your traffic flows inside the VPC. Most of the time, they're kept pretty simple. Sometimes they can be complicated. So, for example, you could change it to say, look, the only local traffic is my subnet traffic, not my VPC traffic. So most of the time, most enterprises will lock down the route tables a lot more than the default way that Amazon does it, so they can control who has access to what subnets. My general recommendation is if you're doing a multi like account model, you can just keep it the way it is, because the only people who are going to get in and out of your account are people who are supposed to be in the account. If you have multiple projects working out of the same account, then you got to go to a multi VPC model, and you might even have them in the same VPC. And so in general, I would avoid that. There's definitely ways to approach that, but in general, the more configuration you have to do, the more complicated you're going to make your life. Use like an organization with multiple accounts instead of doing a lot of configuration on the networks. Now, public subnets we already talked about, they have an attached internet gateway. If we look at private subnets, guess what? They do not. They do not have an internet gateway. So traffic is just going to stay local in a private subnet. Now, I say that there is a way for you to get a private subnet to route into a public subnet and then get out to the internet. That's called a NAT gateway. We're going to talk about that in a second. Now here we have default Amazon VPC. So one thing I may have mentioned is that every single region, every single account has what they call default VPCs. These are like created when you provision your account, and they're just there so that you can launch resources quickly. So Amazon's trying to make it easy. They're always like 172 addresses. They're always /16s. They're already configured like to allow traffic in and out, to allow traffic to get to the internet. So don't get too hung up on them, but just know that they're there. General rule of thumb is don't use the default VPC unless you're just messing around, like you're doing a proof of concept or something. Otherwise, please, please do not use the default VPC for production traffic. You need to do a little bit more configuration to really make that work for most environments. Do not delete the default VPC. They will allow you to recreate it, but it used to require a ticket to support. But they're going to recreate it anyway if they make any changes to the VPC. So you might as well just leave it. Now, multiple VPCs are cool because you can separate it out. As you can see at the top, you can create VPCs on a per environment basis. Most people don't do that. What they're going to do is they're going to create multiple accounts. And one of those accounts is going to be prod, one of those accounts is going to be dev, and one of those accounts is going to be test for a single product. This also avoids a bunch of things like service quota limits and all kinds of stuff. You get better granularity control. And if you combine this with organizations, I personally think the multi-account model is by far the easiest enterprise model to use. That being said, you still have to know how to configure VPCs and make public and private subnets. Now, if you want to make an instance publicly accessible within a VPC, I mentioned this before, you have to basically use it on a public subnet, and you have to basically give it an IP address. So, update the route table, make sure the internet gateway is attached, make sure the route table points towards the internet gateway, and then make sure you assign the EC2 instance a public IP address. Questions that commonly come up in the Solutions Architect Associates level exam is they'll say, we've attached an internet gateway, we've updated the routing table to point towards the internet gateway. What's the last step that we need to do in order to enable this EC2 instance to talk to the internet? And the answer is assign the EC2 instance a public IP address. So just be aware that does pop up frequently as a question on the exam. And Christian, I saw that you said you use both, where you do a multi-account model and you do a multi-VPC within that multi-account model. Yeah. The only other division I've seen is where they'll do multiple account, but they'll put like product A production in its own account separate from product A, like non-production accounts. But again, I think as long as you're doing some combination, I think you're probably headed in the right direction. The main reason people do it that way is also that it's easier to do billing that way. It's easier to do like cost attribution. So, okay. The other thing that you can do, other than just using public IP addresses that are auto-assigned from the Amazon pool, is you can statically assign IP addresses to resources. Now, an example of this would be basically using what's called an elastic IP address. This elastic IP address allows you to assign a static IPv4 address to your EC2 instance. And the cool thing about this is that until you terminate that instance, that IP address is never going to change. If you use the auto assign method, which is the default inside of a VPC, when you assign an IP address, it's going to come from a pool, but it's going to have a lease on it, which means it's going to expire and change and get renewed. Now, you may not care if, right? You may not care because it's not a static resource, or you have a way of tracking the IP changes, or you're using DNS or something like that. But just know that if you need to have a static IP address, you're going to have to use an elastic IP to make that happen. Now, Amazon, limits you initially to 5 elastic IP addresses. This is just a service quota limit that you can easily lift. So just know that you can request more IP addresses if you need it. Okay. One other thing worth mentioning is that most of these IP addresses are pulled. All of them are pulled from Amazon's public pool. Be aware that if you want to bring your own IP addresses, you can. You have to, change the attribution and set a bunch of things, in Aaron and all this other stuff. It requires a significant amount of configuration, but you can actually assign and route your own public IP addresses into Amazon if you want to. It's all up to you. Oh yeah, it does say that, doesn't it? Okay. We mentioned before is that what if I'm on a private subnet and I want to talk to the internet because I want to retrieve patches or internet software or some variation thereof? Is there a way for me to do that without having to put that resource out on a public subnet? And the answer is, of course. So at the cost of 10 cents an hour plus whatever data you shove through at a per gigabyte charge, which is usually pretty tiny, Amazon will let you run what's called a NAT gateway service. This NAT gateway service sits on your public subnets, and it allows you to run your traffic from that EC2 instance through the NAT gateway, which will act as a proxy for you to get to the internet. This is only for outbound traffic. You can't use this to initiate connections in from the internet into that EC2 instance. You can only go outbound on that traffic. So NAT is designed so that you can conserve IP addresses, because you're going to have to assign a public IP address to that NAT gateway, but that's it. A bunch of services could use that NAT gateway to get out to the internet. I actually prefer doing this with a NAT gateway instead of putting my resources on a public network. Now, I say that. You could actually stick your EC2 instances on a public subnet and just not give them public IP addresses. You heard it here first. Right? You don't have to stick things on a public subnet out on the internet. They can just sit there with private IP addresses and have access to the internet. I know that sounds strange, but just because an EC2 instance is on a public subnet doesn't mean it has access, the internet can get to it. So just keep that in mind. NAT gateways, by the way, are services. So it's just like an internet gateway in the sense of that it is at least availability zone redundant. Now, how much bandwidth can you run across a NAT gateway? It's funny that I asked that question, because I don't know that I've asked it before, because I actually don't know the answer to that. I'm gonna have to look that up, actually. I don't remember off the top of my head. But unlike the internet gateway, which has no limits, the internet gateway does actually have some kind of limit to it. I don't know exactly what it is, but I think it's in the terabytes, but terabits, sorry. But I'd have to look that up to be exact. Now, it's a lot. Let me just put it that way. It's a lot. It's usually far more than people need, but I've got to look that up at our next break and see what that is. Now, notice here, if you look at the route tables, that the public route table for that public subnet lists an internet gateway at the bottom. If you look at the private route table, which is in the lower right-hand side, note that instead of listing an internet gateway, it lists a NAT gateway ID. That's a little different, isn't it? So in this case, what happens is that in both cases, you have what's called a default gateway, but one on the public subnet refers to the internet gateway, on the private subnet is referring to the NAT gateway. So to highlight this a little bit further, notice that this subnet is going to look at this table, which says go here, which says go here, which says, okay, let's go here. Note that this route table, it says, hey, I want you to go to this NAT ID. I want you to talk to this guy. This guy is trying to get out to the internet. It looks at its route table and it says, oh, it wants me to go to the internet gateway. Got it. The internet gateway says, hey, you want to get out to the internet? Let's go this way. So note in that setup that these route tables are extremely important for determining who is going to flow towards what. Good. And that's a NAT gateway. So this is how you connect private subnets to the internet for outbound traffic only, right? So notice that NAT gateways managed by AWS prevent private instances from receiving inbound traffic. Someone take a guess for me. We haven't talked about them at all. If I wanted to receive inbound traffic, instead of using a NAT gateway, what do I use instead of a NAT gateway? I'm not sure. Oh, Timothy, you were talking about transit gateway. No, transit gateways are actually not for internet traffic, but I'm glad that you know what transit gateways are because we're going to talk about those, right? Transit gateways are only for VPC to VPN to direct connect traffic. But I'm heartened that you wrote that. It actually, I had to sit there and think about what a TGW was for a second. But no, transit gateways are not used for that. Inbound traffic on the internet actually uses load balancers, right? A reverse proxy, a load balancer. So load balancers are devices that take internet traffic that you hit, the internet comes in, and then it distributes traffic across a bunch of EC2 instances. I just mentioned that because NAT gateways are for outbound traffic, load balancers are for inbound traffic. So don't expect to be able to take inbound traffic on a NAT gateway. You can't. And don't expect to initiate outbound connections on a load balancer. You can't. Okay. So notice here that we're back to our original picture, and here our VPC is spanning across two availability zones. Now notice, by the way, that our picture has what we were just talking about, but not really discussing, which is that there's an elastic load balancer here. That load balancer, by the way, is distributing traffic to these instances. And don't worry, we're going to talk about these. We're not going to talk about them right now, but we are going to talk about them, right? But notice that when the app servers initiate traffic, and I'm going to put this in green so you can see it, they're going to talk to the NAT gateway, which is going to talk to the, right? And it's going to talk out to here. So notice the different flows of traffic. Now, I just want to mention, by the way, when the app servers are responding to a request, they're going to respond back to the load balancer. But this is not new traffic, just to make sure that we're clear about this. They are responding to an existing request, right? So when these guys respond, they're coming back on the same pipe that the request came in on. Okay, so these servers are going to respond exactly along the same path back to the load balancer. Wow, white is a horrible color for that, isn't it? Sorry, not sure what I was thinking. So remember, elastic load balancers are from internet inbound traffic. NAT gateways are for outbound to internet traffic. Okay. So remember, those devices are used for very specific purposes.
Got a question for you. That brown dashed rectangle
Mhm.
represents, is it the subnet?
So no, this represents the auto scaling group, which is going to add and remove boxes.
Oh, gotcha.
Right? It's going to add and remove boxes as needed, right?
Oh,
Down here and
gotcha.
down here. That's what that is supposed to delineate.
Gotcha. So both those instances, although it says app subnet, so but these are different subnets, correct, sir?
Yeah, and to clarify what they're trying to emphasize here, the app subnet and the data subnet are private subnets.
And those are different subnets.
Those are all different networks. Yeah.
Gotcha.
Yeah. So this whole thing here, this whole thing here, this whole thing subnet here, and this subnet here are all private subnets.
Gotcha.
And they're in two different availability zones. Yeah. Good. Okay. Now, in addition to having elastic IP addresses, by the way, do you get the sense that Amazon likes elastic? What a surprise, right? So in addition to having elastic IP addresses, which are just IP addresses that are static that can be assigned to a network interface or a virtual machine, in addition, we have elastic network interfaces. We also have elastic network adapters, and we also have elastic fabric adapters. I know. The meta goes deep, right? It's like a video game. It's like a good book. It just keeps going down, right? So notice here that also when we have there's this like a security group here. This little stateless firewall is wrapped around a network card. So something to be mindful of is that security groups, which are stateful firewalls, are by default around every network card you put into AWS. So if you start a virtual machine, which always has at least one network card in it, because otherwise, how would you get to it? It always has a security group around that network card. Now, that security group could be wide open. By default, it is locked down for inbound traffic, and it's wide open for outbound traffic. Okay, that's the default. So this security group, oddly enough, actually wraps around this entire thing. So this security group actually wraps around this entire instance, right? So just know that you have to have a hole in the firewall in order to get to this thing, but it can get outbound by default. Now you can lock it down, by the way, so it can't get outbound to anything. And then I would ask you why you have it. So when you do an elastic network card, though, like an elastic what's called an ENI, like a network interface, you keep the same MAC, the same IP, private IP address, and the same like elastic IP address if it's assigned. So if that card gets moved around to another system, it's going to keep the MAC address, keep the IP address, and keep the private IP address. So public and private is supposed to stay. Christian, let me clarify something because I just want to make sure I understood you. You said also EKS. Could you clarify that for me? I wasn't sure if I understood that. Oh, yeah, Elastic services. Yes, the Elastic Container Service, the Elastic Kubernetes Service, the Elastic Transcoding Service. You are exactly right. They really like Elastic. One other thing to mention.
Here, though.
Oh, go ahead, Vanan.
Sir, here, you're right. They like Elastic, but here, sir, here, when you say Elastic IP address, I thought you also mentioned that it maps to a static IP address, right? One.
It is a static IP address. That's what an elastic IP is.
So that's like that's like a misleading name, right? Elastic IP address.
Well, it's elastic in the sense of that you can move it around, right? So it's flexible in that way. But you're right.
Okay.
It's not dynamic. It's not a dynamic IP address.
Oh, gotcha.
Yeah. The other thing worth mentioning is that since every single virtual machine has a primary network interface that you can never remove, one thing people think is that if I add additional network interfaces, it'll make the EC2 virtual machine faster. Just so you know, adding more virtual machines like network interfaces to a virtual machine does not make that virtual machine faster. The backplane on that virtual machine is actually limited by the backplane, not by the network interface. So if you buy a machine and it says it has 10 gigabits of access, you could add 10 network cards to that thing and it wouldn't actually go faster. It's going to be limited to 10 gigabits of access. Okay. So just something to know. The main reason to add network cards is because you're either running into an operating system limit or you just want to create some kind of management pathing, right? So just keep that in mind.
What did you say that every VPC has primary network that what?
Every EC2 instance has a primary network interface that cannot be removed.
Oh, I see.
Right, because if you remove the last network card off of a virtual machine, nobody can manage it, including AWS. So they don't let you do that.
Gotcha. Thanks.
Yeah. Hi. Hold on one second. There we go. All right. Now, all of this has been IPv4 based. So remember that whole IPv4 versus IPv6 that we were talking about at the beginning? Do note that they do have an egress only internet gateway. This is also a managed service, right? Just so you're aware, horizontally scaled, highly available, highly redundant. This will also act as an IPv6 egress gateway. So the other internet gateway, the standard one, is actually for IPv4. The egress only gateway is for IPv6. So just note, I don't know why they didn't just call it an IPv6 internet gateway. For some reason, they decided to call it an egress only internet gateway. It doesn't even have IPv6 in the name. So if you get an exam question and it says, you need to enable outbound IPv6 address from your networks, and it says, how do you do that? One of the answers is an egress only internet gateway attached to your VPC. That's the answer, because that is the only way you can get IPv6, outbound, right? So it's going to facilitate communication from your instances to the internet. By the way, this is going to prevent initiation of IPv6 connections into your instances. Notice that there's no NAT or NAT gateway required for IPv6 traffic. You don't need that, right? Why is that? Does anyone remember why there's no such thing as a private IPv6 subnet? Does anyone remember why that is? Christian, I suspect that you know, since you were making comments about this earlier. Timothy, you're definitely not wrong. 340 trillion IP addresses, right? So the thing to know about IPv6 is that IPv6 doesn't have private addresses. So you can't create a private subnet. Now, don't get me wrong. You can create an isolated subnet. It doesn't have to be available to the internet. But there's really no such thing as a private subnet, right? There's only isolated subnets. There's no such thing as private ranges in IPv6. And IPv4, which is the 10 and the 192s and the 172s, those are reserved for private IP use, right? So
how do you achieve the private subnet type capability?
You just create a subnet, which, by the way, is all going to be IPv4 based anyway, but just create a private subnet, make sure it's enabled for IPv6, and just don't connect it to an egress only gateway. So it's going to eat IP addresses from the IPv6 ranges, but you're not going to allow them to talk to the internet. That's the only distinction. Yeah. So because there is no private range, so you're just going to borrow one of the 340 trillion addresses. So. Okay. So the main thing to remember from this is that remember that the different components, right, starting from VPCs, is that you've got a VPC, you've got subnets. Subnets are slices of a VPC, right? So you're going to subnet these things out. This is all pretty much IPv4 based, right? So we're not talking about IPv6 per se, although you can attach IPv6 to any of these networks. You're going to subdivide those out, and then you're going to attach an internet gateway to your VPC so you can get to the internet if you so choose. And if you attach a route inside the route table for a subnet to the internet gateway, then that's now a public subnet. If you attach an IP address to an instance in there, now you got full connectivity to the internet, assuming the firewalls are all in alignment. So let's be clear, we haven't talked about firewalls yet, but there's a bunch of firewalls here. In addition to public and private subnets, we talked about the existence of default VPCs, and then the benefits of a multi-VPC, multi-account, or a hybridized model, and then how to make an instance publicly available, which requires an internet gateway, a route from the subnet to the internet gateway, and a public IP address on the EC2 instance for it to work. So you got to have all three of those things, and that's not including the firewalls, which we haven't even talked about yet. And then you can get a static IP address using an elastic IP versus a changing revolving IP address. And that if you need to get a private subnet out to the internet, you can use what's called a NAT gateway service. And let's see what else. There was one other thing. Oh, the elastic network interface, of which I told you there's also an elastic network adapters. There's also elastic fabric adapters. We'll talk about those later. And then the egress internet only gateway, egress only internet gateway, which is an IPv6 enabled gateway. Remember, you can stack IPv6 on any of these VPCs, on any of these subnets, and then turn on this gateway if you want to have, in and outbound connectivity. Remember, for any subnet to ever get to the internet, whether it's IPv4 or IPv6, the route table has to have a default gateway in it in order for it to get to the egress only gateway or to the internet gateway. Okay. Questions of any type? All right, victory trumpet. All right, let's go on to VPC traffic security. People are like, what was that? It's Christmas, just bear with. Or holidays or Kwanzaa or whatever, right? Hanukkah, let's not all forget. All right, so defense in depth. So I kept talking about the firewalls. I kept hinting about the firewalls. You're like, Jesus, Forrester, when are we going to talk about the firewalls? And I'm like, you know what? Maybe we'll talk about them now, actually. So note that this is a great little map that shows the flow of traffic in to a virtual machine, and it shows the flow of traffic out of a virtual machine. So the breakdown is that when traffic is initiated in, it hits the internet gateway, reads the route table for the VPC, right? Because the VPC's got to say, hey, you got to go this way. Then it has to get past the subnet firewall, which is that network ACL. Then it gets inside the subnet. Then it has to get to the security group firewall, which is attached to the instance. And then it gets to the instance. In response, it goes exactly the reverse. Hit the security group, go to the public subnet, look at the route table, hit the internet gateway, get out to the internet, right? You might say, Michael, hold on, wait. The network ACL is a firewall for the subnet? Yes. And the security group is a firewall for the instance? Yes. That's exactly right. Now, the network ACL, sometimes referred to as a NACL, which I think is actually proprietary to like Cisco or something. Note that there are rules that say, hey, inbound traffic is allowed in if it matches this pattern, and it's allowed out if it matches this pattern. Notice that both with the inbound and the outbound rules, I want you to notice something very specific. There is a deny rule at the bottom of each of those rule sets. If traffic does not match any of the preceding patterns, any of the preceding rules, it is denied, right? Now, this is not the default for like a default gateway. The default gateway by default will allow traffic in and out regardless, right? So the other thing to know is that other than being explicitly rule-based, which either is going to allow or deny traffic based on traffic patterns, these network ACLs are very simple. In other words, if Christian and I are having a conversation and he has a rule that says that Michael can talk to me, but he doesn't have a rule that says that he can talk to me, In other words, he's got a rule that says Michael can talk to Christian, but he doesn't have a rule that says that Christian can talk to Michael. We can't talk. Be like, hey, Christian, and he can't talk back to me. Because stateless firewalls do not track who initiated the connection and then assume that you can respond. Stateless firewalls require explicit rules for both request and response. So if I'm talking to Vinod and I say, hey, Vinod, hi, can I talk to you? And Vinod has a rule that says that he can talk to me. We got two rules, one that allows me to talk to him and one for him to talk to me. We can have a conversation. Right? And that's because stateless firewalls do not track who initiated the connection. They evaluate each traffic independently as it goes, right? That's completely different, by the way, than a security group, which is stateful. So with a stateful security group, if I start a conversation with Christian and Christian has a rule that says Michael's allowed to talk to me, the stateful firewall realizes when I've initiated a connection with Christian and then allows me to respond on that same conversation. If I'm talking to Christian and he has a rule that says, hey, we can talk web or we can talk, FTP, which would be weird, but let's just say that's the case. But Christian has a rule that says we can talk web, but we can't talk FTP. If I talk web to Christian, he can respond to me. But if I try to talk FTP to Christian, he can't. Oh my God, TFTP. Please no. So, just know that with a stateless firewall, you have to have explicit rules to both request and respond. So to initiate and return, you have to have rules for both. For a stateful firewall, which is what a security group is, you only need one rule. Who can initiate the conversation? That's all you need. So here, notice that the rules, and they're a little weird because there's no response rules down here on the outbound traffic, which is a little strange because without response rules, that's going to be really tough, right? Just know that there normally would be response rules. So if there's an HTTP rule up top, there'd be another one on outbound, but they didn't do that for the example. I don't know why, but they should have, right? Now, rules are evaluated in order, by the way, and the minute you match one of the rules, you're allowed or denied. So just, be careful because rule order and rule precedence does make a difference with stateless firewalls. Most people don't even really mess with stateless firewalls unless they're really deep into security, which is actually most enterprises. So that sounds like I trivialized that. You'd be surprised. Some startups just focus on security groups. They don't actually touch the NACLs. Now, NACLs are the stateful firewalls. These are the ones that require one rule to initiate a initiation and a response. So request and response just requires one rule. Now, rules are evaluated. All the rules are evaluated. So if there's a match, it will it'll take it, right? One thing that's worth noting also is that by default, all traffic is allowed outbound and traffic is denied inbound. So, when it asks you questions like that, and you can control it by port and IP address, and is it TCP or UDP or ICMP, you get to control it. One thing to know about security groups, they cannot deny traffic explicitly. They can't deny slices of traffic. They can allow slices of traffic. So security groups really only do allows for the most part. I think they were going to change that. I don't think they can do denies just yet, but there was some talk about them getting that feature. Let's go take a look at this really quick. Oh, wait, it was right there. Where did I go there? Let's go take a look at this inbound, outbound rules. Yeah, they're still only doing allows. They don't actually have any kind of customizations for denies yet. So they only allow allows, and they've only been doing allows forever. Elastic graphics. Yep, cool. So that can just a reminder, security groups will only allow traffic. They won't deny traffic. If you got some guy in, Colorado who's trying to hack your server and you want to allow the whole internet to get to you, but you want to deny that person's specific IP range, you have to use a network ACL. Because remember, they have denies, right? You can see denies right here. Okay. But state security groups only do allows. So you can't exclude a range with a security group. Okay, so those are the two firewalls, NACLs and security groups. Security groups are stateful, NACLs are stateless. I think I already talked about the defaults, which is it allows all outbound traffic and blocks all inbound traffic. You can create custom security group rules. One thing that's cool about security groups is that you can allow traffic to and from another security group. So if you want your app servers to only allow traffic from members of the web server group, you can do that. If you want your database servers to only allow traffic from the app server group, you can do that too, which is actually pretty cool. So you can literally chain them together and make it so that if someone's not a member of the security group, they can't actually get access to your service, which is pretty cool. So this is the original thing that we were looking at. Hopefully that makes more sense, is that NACLs wrap around an entire subnet. Security groups wrap around an instance. Security groups are the stateful ones. NACLs are the stateless ones. If you were going to take the exam, the certification, I would memorize this to a certain degree, right? Okay. Questions about VPCs and the firewalls? Okay, here's a question. A single Amazon VPC can span multiple regions. Is that true or false? Sean, they're good. Timothy, Masood, Hunter. All right, looks like it's unanimous. It is indeed false, right? You can connect VPCs in other regions together using VPC peering, but a VPC cannot span a region, like multiple regions. It can only eat an entire region, a single region. Cool. What action must you take to make a subnet public? What? There were 3 steps to this, right? But what's the first one? In order to make a subnet public, it is indeed C, route to the outbound traffic to the internet gateway. All right, next question. What function does a NAT gateway serve in relation to subnets, a particular type of subnet? Cool. All right. Allows internet traffic initiated by private subnet instances. That is 100% correct. Good. Remember, that's what a NAT gateway does, is it allows private subnets to connect to the internet. What should you use to create traffic filtering rules at the subnet level? Boom, 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 boom. Good. Looks like there's some consensus there as well. It's network ACLs. Excellent. Okay. What is open or closed by default when you create a new security group? Which is open and which is closed by default? Which two? Two of these. Nothing is allowed inbound and anything is allowed outbound. A and D. Those, I see those answers. Spectacular. Okay. That is the end of module 3. Questions about VPC networking, subnets, IPv4 versus IPv6. That's true. It's funny because most hacks are internal, but if you're using multi-accounts, Christian,
So I have a question, a general question on VPC.
yes.
Are there like a default route tables or default like network ACLs attached to a VPC that you cannot remove? Well, here is the premise why I'm asking. I was for a task, I was asked to delete these default VPCs, and I know you said you don't need to, but that was the requirement that we need to delete them in a particular environment. And so I wrote a rule. So I had to delete, security groups. I had to delete internet gateway. If there were any EC2 instances, we removed them. And that was all needed. But I was trying to see like if there is any network ACL. And apparently there was, but when we were trying to, and also there was apparently some route table association, something like that. So all the default one, it wasn't letting us delete. However, that did not stop us from deleting the VPC.
Right. Well, because every VPC must have at least one route table associated with it, and every subnet has to have the NACL associated with it, right? You can change the rules, but you can't delete the firewalls unless you delete the object itself, right? Like you can't delete a security group off of an EC2 instance or a network card. You have to delete the network card or the EC2 instance.
I see.
Right? Now, don't get me wrong. You could apply other security groups to the object in question, but it has to have a security group assigned to it because Amazon will not let you not have security or a route table on an object. So it would make sense that you could delete the object itself, but it wouldn't let you delete its like base configuration. Like you couldn't change the route table, you couldn't delete the NACL. You actually have to delete the objects.
But it was allowing us to delete default security group,
right?
But not the NACL.
Well, and there were probably no objects for the security group to be attached to, correct? Because you had deleted all the EC2 instances and everything else.
Yeah.
But it wouldn't let an object exist. It wouldn't let you do that if it was associated with an object. You would deleted all the objects first, right?
I see.
But the last thing that you were left with was probably VPCs, like a VPC, and it had to have a route table, and it had to have what was the other thing you were talking about?
NACL.
A NACL, right? So it's not going to let you delete those.
Oh, gotcha.
Because it's the last thing required by the object that you're trying to manage.
Gotcha. But I can, at that point, I should be able to delete the object, which was VPC, and it allowed.
Right. And it should have let you delete the VPC.
Great. I think that explains a lot. I think, although nobody asked me why am I, so I had to bypass. Basically, I had to bypass if it is the NACL, the default NACL or default route table association. I think it was a route table association, I believe, something of that nature. Then it was not deleting, but it was still allowing me to go ahead and delete the VPC.
Right.
Anyway,
yeah.
Thank you, sir.
Yeah, that makes sense. Okay. Good question.